Great. Welcome. Hi, everybody. Welcome to our Openscapes Community Call. We are recording and we'll post this on YouTube, and a transcript is available for you through Zoom right now as well. I'm Julie Lowndes. I'm the director of Openscapes, and there's a huge effort to put this community call together. We're joined here by the Openscapes core team, if folks want to give a wave, as well as Openscapes mentors from NOAA and NASA, California Water Boards, and otherwise. So welcome. We're here to help. Openscapes is an open source approach and a movement. It's really become a mechanism to help research teams find each other and feel empowered with modern data-intensive science workflows that we're building together. All Openscapes activities are bound by our code of conduct that is linked in the doc, which Stephanie is putting in the chat, and we encourage you to write into. Some highlights from the code of conduct are to be respectful and value each other's ideas, styles, and viewpoints, and lead by example and match your actions with your words. If you need any help during the call, please direct message Stephanie or myself. Our plan for today is to celebrate earthaccess. Earthaccess is a Python library helping users leverage the awesomeness of NASA Earthdata. So we will be sharing talks that the NASA Openscapes mentors prepared for the ESIP summer meeting last week, but were denied participation at that event. So our first hour of our community call together, we've designed this as an hourglass shape. We will start with stories for you to hear and get inspired by and turn around and retell. We'll share exciting new technical development and features, and we'll end with a vision going forward. We know that this audience is very diverse in your experiences and your interests with earthaccess, and so we're covering a breadth of information here. This first hour of the community call will be recorded. Then we'll have 30 more minutes not recorded for an open mic time and discussion. So you'll be able to share your questions and your stories with earthaccess as well. You're also welcome to write in the doc at any point or in the chat. We'll be helping curate your questions and comments in the doc so that we can build this rich resource together. So we welcome your participation that way. We have amazing speakers today. Their bios are in the doc. I won't read them all out loud, but know that Amy Steiker, Luis Lopez, Danny Kaufman, Joe Kennedy, and Chris Battisto are all here and are going to share their amazing stories. So with that, I'm going to pass the mic to Amy Steiker from the National Snow and Ice Data Center, the NSIDC DAAC. And she is going to be sharing about crossing the chasm. Go ahead, Amy.
Awesome, Julie. Thank you so much for the great intro. I will jump in and start sharing my slides. You can find them linked to the doc as well. All right, so thanks again to everyone who is here today. Thank you, Julie, Openscapes core team, for supporting this. So we are just so excited to share with you today. As Julie said, we're really here to kind of celebrate us. There's a lot to celebrate. And this just felt like a really good kind of moment. This talk, we're kind of going to zoom out a little bit and talk a bit about kind of the story of earthaccess, kind of where we're at today in the context of just a lot that's changing, the context of kind of NASA Earthdata evolution, and kind of talking about this concept of crossing the chasm. So again, I want to acknowledge Julie Lowndes, who really helped to facilitate and help us frame the story that we wanted to give today. And so starting off, when we're talking about crossing the chasm, first of all, this was a talk that we were planning to present at the Crossing the Chasm session at ESIP last Friday. That session still went on, but this talk specifically about earthaccess, we were not able to share that today. So this crossing the chasm concept, this was originally kind of presented by Eli Holmes at the CNG conference earlier this spring. And this concept, and we'll reference the author and more into this kind of diffusion of innovation theory in just a moment. But this general concept as an introduction here is that there can be sometimes a very large chasm between an initial kind of innovative idea and those early adopters who kind of sign on to, to kind of promote it and develop it, between that and broader adoption within a wider population within an organization. But this can actually be really hard to define. The concept resonates a lot with the Earth access kind of community. Like, we could see ourselves as having, like, there are potentially lots of chasms. But it's been this really interesting journey to kind of figure out where this fits into the Earth access story. When we think about chasms, right, I think the most notable one that comes up surrounds kind of the Earth access like origin story in a way. And I this slide also hopefully is helpful for those of you who are less familiar with Earth access to kind of give a little bit of background on kind of the Earth access origin a bit. So the story really starts with the NASA Openscapes mentors several years ago, and we were sort of tasked to help users in their migration to NASA Earthdata Cloud, whatever that kind of means, in sort of this big nebulous way. What does Earthdata Cloud migration mean? So that was a big chasm initially between users and NASA Earthdata Cloud. And so Earth access kind of came about, but was enabled by NASA Openscapes mentors that sort of broke down organizational silos and really dug into, like, what does success mean? It's one thing to kind of set up a distribution endpoint in the cloud, but, like, how do users actually access it, right? Before the Earth access Python library, users really had to understand the complex kind of backend architectures around the NASA Earthdata system, right? Thinking about how to format searches across different NASA data centers, different credentials across those data centers, actually having to switch their code between whether it was in region or not, whatever that may mean, and having to understand the complexities of cloud-based object storage as well. So Earth access kind of came about and was developed as this sort of bridge to help that chasm, right? Now Earth access can help enable search and access regardless of NASA Earthdata, regardless of where your compute is located. There's these 3 basic lines and steps in that workflow to log in, to search by DOI or any other kind of search parameter or filter, and then directly take those results and open them, in this case, in an Xarray data set. So that was an initial kind of success, right? So we kind of thought of Earth access as this bridge, this initial kind of bridge. The shift now, sort of thinking about kind of where we are in the moment, is kind of thinking about, well, it's not necessarily about Earthdata Cloud. Of course, it is in a lot of ways. We'll talk today about a lot of innovation in the space of more large-scale performant access, virtual data cubes, et cetera. So this is absolutely still relevant and continuing to kind of work towards those broader needs. But we're now kind of flipping and changing the story a little bit and thinking about how at a larger scale are we helping users to leverage the awesomeness of NASA Earthdata, right? Like, that's our kind of theme of today. So going from that kind of those early adopters, even within the Earth access kind of community, and thinking about what does that broader, larger target population look like? And now the shift is really thinking about how do we not only sustain the bridge, but continue to sort of build it, expand upon it, add spans or more robust structures around that bridge. And that's really where we're kind of reframing and asking ourselves about kind of where to go next here. So pausing kind of for a moment here on, like, how far we've come when we think about the initial kind of Earth access early adoptership, and how we started off to kind of support users migrating their workflows to the cloud. It's become so much more. It is very easy to brag about all the amazingness in the maintainer and contributor and user community within Earth access. This is just one story in the top right here. of a NASA SMAP mission PI who says Earth access is amazing. For this researcher, it has been integral to his open science climate curriculum, where he's teaching students about how to apply NASA Earthdata to real world agricultural applications. And like I said, this really wouldn't have happened without Earth access. We have over 200 dependent projects now where Earth access is a dependency in those libraries, projects, repositories. Some of these are big, popular core geospatial packages. We have over 500 GitHub stars, and that's a lot, I would say, and it's increasing very steadily. We now have a page on the official NASA Earthdata website, kind of highlighting Earth access as a core tool. And so I'll kind of segue a little bit in terms of kind of what we've done to enable that. We started with these hack days about 1.5 years ago. These are bi-weekly. We can add, I think there are links already, and we can add more information about if you're interested in joining those. So again, these take place every other week. They've continued for 1.5 years now. They're 2-hour blocks where we can come together and co-work, code, review PRs, talk strategically, all the things, and welcome new people who are just interested in getting to know the community. And so we can, Earth access as a whole is reproducing or enabling that reproducibility of workflows, collaboration, and transparency. So I feel like this is kind of the core focus here, the crux, if you will, when we think about kind of where we are today and how to continue to grow this and build upon this bridge. We have built Earth access with this intentional culture and community. And we find that it's sort of critical to its success so far and its future growth. And I'd even go as far as saying critical to the success more broadly across NASA Earthdata, and just in the overall kind of goal of improving Earth data, Earth science workflows for everyone. We are facing new challenges. So I think we've all been affected by this. It's not news, right? There are budget concerns, uncertainties. Right now in the Earth access community, we still do not have sustained kind of funding, at least within NASA Earthdata. And that can be tough, right? Like we've had those challenges and we've had to think about ways around them. But I really want to pause here and say that these, what I consider kind of small ways to sort of tap into existing enthusiasm, right? Like have a place where people, whether it's grad students, others in academia, other partnerships as we've listed here, like within X-ray, the Pangeo kind of ecosystem, other data kind of organizations, just having that opportunity to kind of say, hey, if you're interested in helping as sort of a win-win, you're already sort of working on the same problems we're trying to work on, we can enable faster development, right? We can like reduce cost. These concepts are not novel. We know that open development can enable these things, but we're seeing this in real time right now. And I think ESIP is a really perfect story here, where again, as Julie mentioned, last week, several of us were not able to join sort of on behalf of NASA, but we had these partnerships that were already sort of set up and being fostered, right, within our community. And what we were able to do there through Julie's leadership, and again through the ways in which Julie and others can kind of connect, she helped Earth Access to secure a small grant through the Funding Friday effort at ESIP, which is amazing. That wouldn't have happened without those partnerships. So it's just an awesome real-time success story. I'm going to pause there. And I think because we wanted to show that pitch at the Funding Friday session that occurred, because it's really amazing. So I'm going to pause, and I think Steph is going to share that, and then we'll head back to the slides.
And I'm going to preemptively apologize for subjecting you guys to my singing. Or lack thereof.
All right, here it goes. And give me a thumbs up that you can hear it when it starts.
Yeah, me too. Okay. Okay.
Hi everybody, we are earthaccess and we are growing the family. We're seeing the whole world. In separate catalogs, we are seeing that.
We've got NASA Earthdata.
In our hands, we've got an open contributor community. In our hands, we see how we see this whole world. In separate catalogs, we like the whole world in our hands. Okay, here we go. We want NASA, NOAA, and Mars. In our hands, we want USGS stack. In our hands, we want Copernicus stack. In our hands, we want the whole world in our hands. We want a hack day at AGU. In our plans, we want a prototype in an afternoon. In our hands, we want the roadmap in an afternoon. In our hands, we want the whole world in our hands. Okay, thank you, earthaccess. Earthaccess is a Python library that enables authentication, search, and access for NASA Earth science data with just a few lines of code. We see great potential for growing the family to include data from NOAA, USGS, and Copernicus, and we would like to use funds for a hack day, both virtual and in person, at AGU in December, and we expect a workable prototype and roadmap in an afternoon. Thank you very much.
Amazing. So great. Okay, I'm gonna go back to my slides now. I don't even know how to keep going after that. Okay. Thanks again for sharing stuff. Yeah, so again, real-time kind of success story here. So kind of going back to, and just wrap up with a few more slides and we'll hand it off and start talking about other cool, fun things going on. So we talked about kind of this concept of this chasm. And this is part of, and this concept, I should say, sorry, is, there was a book written by Jeffrey Moore. Sorry, your faces are in the way, so I'm missing the author, by Jeffrey Moore. And within that is, again, this diffusion of innovation theory, which is kind of talking about, again, the sort of innovators, maybe some initial smaller chasm to get to early adopters, a big scary chasm in question, and then getting to the majority. So as we're talking about kind of bringing it all back together now, thinking about earthaccess as this bridge, bigger picture of enabling NASA, like doing cool, amazing things with NASA Earthdata. To get to that majority, we're kind of thinking about this concept of like earthaccess with the batteries included. And thank you to Andy Barrett for that awesome analogy. So what does that really mean? And actually, I'd pose this question for you. Like, what does batteries included look like for the earthaccess library? You know, one thought is, especially as we're thinking about how to meet users where they are, we've been focused a lot on Python workflows. What about other programming languages, stack interoperability, for example, something we'll work on at the AGU hackathon. Even thinking about existing web user interfaces and other kind of components within NASA Earthdata. We've done some prototyping with Jupyter notebooks and code snippets within NASA Earthdata search. Could we expand that on the NASA Earthdata landing pages, right? So just as some examples. And again, thinking about widening the bridge. I'm not gonna, this is just kind of a preview, and Luis will kind of summarize this bigger picture vision more in terms of the technical roadmap of enabling real world analysis at scale. So this is sort of a preview of like, again, what is this target population and how can we kind of get over across this curve? But also, I'd say just as important, if not more, is back to that community governance, enabling and continuing to sustain and enable community development. We've been talking a lot in the community about this concept of repotting the earthaccess repo to further enable those partnerships. And for those of you familiar with the kind of cathedral versus bazaar analogy, right? Like how to keep maturing the bazaar and then lowering the barriers to contributions. And we are working towards this through our kind of newly developed decision committee process to move forward on this repotting decision and next steps there. So ending here with just a couple of questions. We'd love to hear from you today, right? Like, how do you build bridges, right? How do we build the bridge within earthaccess and again, continue to expand upon it? How do we increase our partnerships? And really flipping that question of instead of, you know, how can we be supported by, it's really how can we support NASA Earthdata, right? What can we learn from and how can we further stories that already exist? So with that, we are now going to jump into a section now to like talk about all the really cool innovative stuff kind of going on in the world of VirtualiZarr and integration with earthaccess. And Joe Kennedy will kick us off, zooming out a bit and kind of talking about like what do we mean by virtual data sets and in the context of cloud workflows and cloud optimized data. Joe, did you want to share, or I'm also happy to share slides on your behalf?
I think it'll work better if I share because I want to hop to a couple websites.
Sure. Thanks.
Let's see. All right. That looks like it's going. A weird bar. Okay. So my talk at ESIP is actually more or maybe better thought about as kind of the background information of what's going on kind of with virtual access, kind of leading up to what we could then do in earthaccess with it. So I'm going to kind of cover the It's Live project and what we've been doing there. Both me and Louise work on it. And it's a project out of JPL led by Alex Gardner. There's two parts to the project. The half I'm going to talk about is this this goal to provide automated low latency, and we'll talk about what that means later, global glacier velocity. So we want to use all of these satellite missions that I've got on the left here, process pairs of them to generate velocity fields using an offset feature tracking algorithm. We'll talk about that a little bit later too. In the end, the idea is that you should just be able to drop a pin somewhere and get ice sheet velocity measurement. So here's our web page. We have this cool instant global data access tool and a little more featured one that you can go to straight. And what you actually just saw was the data load live from these Zarr data cubes in the background. So that actually happens kind of incredibly fast. So let me clear. Kind of anywhere in the world, there's a glacier. You can zoom in and drop a pin. I always use this one, this big fat pancake. And as I drop pins, you'll see just this time series load automagically in the background. And so that you can get the entire history of the ice sheet velocities back through the entire observing record. So 1984 with Landsat 4 all the way up to kind of now for the optical satellites. And we're working on getting low latency radar going. So kind of what we're doing here, I want to take a step back. We're extracting this time series. How are we doing that? So we got our Earth here. We got a satellite flies by, takes an image. Over time, it takes more and more images and builds this stack over a specific area. If we're lucky, the mission is actually structured in a way that it's always observing the same spot on the ground. We can build these nice stacks of data in some discretization on the globe. And so what we want to do, because we have a derived data set, is generate these velocity pairs from this stack of observed data. That kind of works as a brief overview for here for It's Live, and this is going to be similar for other projects doing the things. But USGS provides a nice topic that says, basically is just a shout that says, hey, there's a new granule. We can do some initial filtering and stuff those messages that there's new granules in a queue. A small, less than 200 line Python script can then kind of process that queue and say, okay, I've got a new granule. Let's look up some metadata in the stat catalog. is it a good granule? Is it over ice? Does it have the right data coverage? Blah, blah, whatever our acceptance criteria is. If it is, it can go and do another search for pairs or images in the same area. So at Landsat, you get an 8-day repeat. If we process images back a year and a half, we go back 544 days. So we'll end up with 64 pairs of images in that stack that we can then process. And all we needed here was just a notification that it's there and a catalog that we can search. So we take those two pairs or those pairs, we send them off to our processing pipeline. I'm not going to really talk about that, but basically what it does is it grabs the scenes out of the USGS bucket in the cloud, does the feature tracking algorithm, comparing the two scenes, seeing where a pixel moved between the two scenes, depending on the time. And that gives us velocities. And they pop out in these potentially 64 different velocity measurements, and we drop them into a public bucket provided by AWS Open So we've got these granules, which we can effectively, let me go back to slideshow so it's bigger. We can do in really rapidly at this point using the cloud. So when the mission acquires an image, downlinks the raw data, USGS processes it, throws it in an AWS bucket and shouts about it. That process takes days-ish. It's like 48 hours typically for Landsat 9. It's up to 2 weeks for Landsat 8 because there's different processing paths, and Landsat 8 is a much older mission. But from the time the topic sends the message and going through that whole workflow that I just showed you, we're talking it takes its live 15 minutes to do that whole process. So we're effectively real time with the mission at this point, generating derived products. That's 15 minutes for all 64 of those pairs at the same time, because we do it in parallel, not 15 minutes each, sort of a thing. So we're doing this a lot, and my whole point is that we don't really need to be thinking about granules anymore. We've made 36 million granules processing the entire archive. We're processing at a rate of about 20,000 a day with low latency. This is just working in the background without much thought right now. And so we're getting to the point where on our project, we're now generating mission-sized data sets. So we want to get this time series. So how is that effectively working? So we can click a point in our web app that then loads in our shapefile effectively that tells us where on the Earth that point is and what data cube we want to get from it. It pulls a time series out of that data cube. Oops. And we get that data immediately, sort of thing. So this works super crazy fast because everything is optimized exactly for this usage pattern. So our Zarr data cube is chunked in time. We have just a really small GeoJSON that can load into memory immediately in the web app, and the web app's just a static website hosted. All of this happens in your browser. There's no API or anything backing any of this. So on the NASA side of the house at ASF, there's something similar that's been done, and I want to walk through it as well. So we have our normal ASF data search portal. If you're using Zarr data, you're probably used to seeing this portal. We now have this displacement portal that loads in the Opera displacement data set. So that's another derived product instead of velocities. Now we're looking at how much the ground has changed up and down. Zarr can do that well because we track phase as we image. So one of the places I like to do for this is Hawaii, because you get this really nice displacement time series. I can zoom in, click a point, and what's happening in the background here is now we're doing a search through the catalog, CMR catalog, and we're selecting all of the HDF5 granules. Well, they're really not CDF, but they're net CDFs with cloud optimized HD5 underneath. We get all this list of granules, and now we're extracting the specific point out of all of those in parallel. And that was actually pretty quick at this point. We've got this whole time series. You see a big displacement event, volcano eruption effectively happened right here. We get that whole time series very rapidly, just extracting data out, but it was noticeably slower. I had to sort of talk over this, and that's because we're actually going out and pulling in individual granules. It's not an optimized cube for this. So this version looks like a web app that's deployed. It's backed by a really thin API that does okay, here's the point. Let's find all of the HDF5s, extract from them, and return that time series directly. There's a couple reasons to do a thin API here. One of the major reasons is that there's auth involved. So if we put the API behind Earthdata Cloud, we can do all of this without auth quickly, and then return the time series. Whereas if you were trying to do it yourself, you would have to deal with auth for every one of those granules, and there would be a noticeable lag. And then we're also planning to do other stuff in the future that the API will handle. And I'll talk about that a little bit more. So we got this web app backed by an API. It's effectively doing the same thing though. There's just an in-memory GeoJSON that lets us know that we've injected into the memory space of the API. It's just living in memory cached there. And it finds the spot on the ground, the specific stack, grabs the stack, and that stack's actually generated each time over time with kerchunk to just give us references to the HDF5 files. So all we're doing is opening the kerchunk, which then goes and opens all the netcdf4s and using byte offset ranges and returns that time series. So we can do this similar pattern effectively with earthaccess, and this is my only earthaccess slide, which is eventually it would be really great if we could just do this ourselves in the community by having these virtual data sets already kind of cataloged and available in the catalog. All we'd have to do is search for the data sets that cover the area and the type of data we want, and then just open them. That's it. Right, and then now we have our ability to pull a time series with XArray or a time slice or however we want to do it. So that's kind of the major big vision. So I want to talk a little bit about where that falls down maybe. So if we were looking at like ITSLI or the displacement portal, I showed time series access patterns, right? Well, if we chunk our data in a time series format, but we actually decide we want to pull an area of interest, a time slice is often what people call it, but a spatial access pattern. Doing that is similar. We just need to know what parts intersect that image. That's not really a difference in the access pattern there, except that when we load the data cube and they're chunked this way, that means we have to load the entire cube to get that spatial access, because each of these chunks gets loaded to cover this area. And so when we talk about cloud optimizing, everybody likes to talk about the file formats. Like this file format can be cloud optimized is really what they mean. File formats or file formats that lend themselves to optimization. But optimization is really about an access pattern. So if you chunk your data in time, you're optimizing for a time series analysis. If you chunk your data spatially, you're optimizing for a spatial access pattern. You can turn this knob, but if you turn it towards one, you turn it away from the other one. And then all of a sudden the other access pattern gets harder. And so you can kind of just put it in the middle and get pretty meh access for both access patterns. So as a data provider, you really need to know how your users are using the data. You can't just provide the data, and you can't just provide a chunk, because you're probably going to do it in a way that's not optimal. So then you lose the benefits of cloud optimizing. And this is a true thing as well for catalogs. We don't talk about it enough, but when we make a catalog, we could make a catalog of a collection of granules for each stack. Oops. Or we can make a catalog that's all of the granules everywhere. And if we, depending on how we choose to do that, the performance of the catalog search and the return and the ease of discovery for users changes. And so this knob also affects how we decide to just show users where these things are. And so if you're a data provider, you've got lots of problems. Like if you have to deploy an app and an API that costs a bunch of money, You've got to figure out how users are going to discover the data, how they're going to access the data. Aligning and chunking the data is something that you really need to think about. And then appending the data, if it's a living data set, is really hard. And I didn't really talk about that at all, but using VirtualiZarr or KerChunk basically means you have to rewrite the entire references each time you want to append, and you get this inconsistent state where you're updating the chunks of data and the metadata, and users are accessing it at the exact same time. So then I'm not going to talk about auth and metrics. We're just going to pretend that doesn't exist, but that adds a whole bunch of other fun on top of this, especially for users. And so we can effectively get rid of the web app costs now by just hosting static sites and doing everything in browser. There's a really powerful combination, DuckDB, a GeoParquet stack, and whatever Zarr-ish looking thing you're using, whether it's an actual Zarr or a virtual Zarr of some sort. Appending is actually the major thing IceChunk, the technology solved. You can actually append to the data and then cut references and get a new state without any inconsistencies for the users. That's the major thing I'm excited about for it. But you can't really get away from still having to think about discovery, chunking, and alignment. And these are kind of things that users really don't want to have to think about, or really shouldn't have to think about. These are data provider problems, or should be. And so like the overall takeaway for my thing is that like these cloud computing paradigms can get us to a place where small teams can generate effectively near real-time mission data of derived products and everything even. So they're producing effectively mission data. We can view these missions as continuous streams of data now, instead of this very download the individual granules, work with them, even access them individually. We really don't need to think about granules. But there's a big if bomb here that I have to drop. And that's all of this only works if the data provider and services and practices align with kind of your access pattern and what you want to do as a community. The cloud business model also has to align. A lot of the reasons that like this was easy for USGS means it's really hard for NASA. And it has to do with egress and what we mean by free and data and that kind of stuff, which gets into institutional policies. And in like the ITSLI project, we've struggled with deploying our stack to Europe because that's where Sentinel-2 data is. And so now we're paying double to egress the data across AWS regions. And because we can't get around the institutional problem of thou shalt not deploy to Europe, but thou shalt also not send money anywhere else because that will cost overhead. And then there's a bunch of community practices, and that in the end, none of this matters if the community doesn't adopt what you're doing. So like as a project, we'd love to grab IceChunk. We probably will start using IceChunk, but we're relying on the fact that the community will support it and use it and understand it. And that's a big if, and that's true in Python ecosystem, but it's not maybe true in R or Julia yet. And we have users in those communities as well. And then that's sort of my pitch, is that we can all work together, but we're here for that specifically, so I can just stop here. And that should tee up Chris and everyone pretty well. Do we want to stop for questions here, or?
I think let's keep moving, and let's go ahead and keep moving. We'll go back to the other slide deck where we'll have now Chris Battisto and Danny Kaufman kind of going into some other use cases, examples, lessons learned, problems, questions that we want to pose related to VirtualiZarr, particularly the integration in earthaccess. So yeah, thanks so much, Joe, for that. It was a great introduction. Chris, would you like to share slides, or I'm also happy to on your behalf?
Someone else is going to have to, unfortunately. So
no problem.
I will go ahead. Yeah, thank you.
Yeah, sure. Okay.
All right, thanks, Amy, and thanks everyone. Thanks for joining us today. My name is Chris Battisto. If you haven't met me before, I'm a senior scientific software developer over at NASA Earthdata. And so what we're going to do is kind of dive a little bit deeper into some of those workflows and access patterns. And then we're going to show an actual use case of it from the user perspective. So I'm going to go ahead and talk about VirtualiZarr and then managing those VirtualiZarrs using IceChunk, which is something that Joe touched on very briefly. Next slide, please. So there's a couple of ways to make an Earthdata cube or a virtual or even just a data cube using Xarray, especially from the NASA Earthdata perspective. So there are several different ways of doing this. No one method is better than the other method. It's like Julie just put in the comments. It all depends on the tool, the application, which kind of governs your access pattern. So you could see method A would be, let's say I want to access my data from a Zarr store. With earthaccess, you can query the CMR. If a Zarr store is available, you can pull those S3 URLs. But for NASA data, at the current moment, you have to be inside of the US West 2 region to access those. So for a Zarr store, you're pretty much set. If you know that your compute instance is sitting right next to that Zarr store inside the cloud, a very optimized access pattern. But you can see we've still got some considerations. If you're outside of US West 2, you might have to figure out some other access patterns for those data. Or if you're in a small scale analysis, it might not be worth it to set up a cloud compute environment, block storage, set up access controls and things like that. But what you're really utilizing here is that scalability that's present. If you click again, we'll go ahead and see another method, which is something that's much more common that you kind of saw already with a lot of our different tutorials or with even accessing things before earthaccess came around. And that's basically individual granule concatenation. So something that folks don't really realize or that might not be apparent is that when you download a bunch of these different granules and you stick them into Xarray, you're creating that data cube. You're just creating it locally. You're kind of bound by your memory. If you're running in 2I2C, sometimes you'll run into this where sometimes you'll need to beef up your instance to a higher amount of RAM. You're also bound to storage. So let's say you've subsetted those granules using OpenDAP or Harmony. You've already downloaded those and they're sitting on disk somewhere. Or you could even stream them using OpenDAP. Obviously, you're kind of bound to whatever configurations or whatever load that remote data server is under. But this is very common, and it's already a great way of managing your data cubes. The only thing is that this isn't necessarily cloud optimized, but that has to do with chunks, and I'll talk about that later. And these are also really great because once that data cube is constructed, you can edit that data already as it's in your session. So if you wanted to export that to a different file format, you absolutely can. But some of those things that have to be considered are those storage spaces and basically where those data cubes are sitting. Because when you export that out of Xarray, you're pretty much still having to export it to a NetCDF4 or to an HDF file, for example. Next slide, please. So that's basically what we're trying to address with this IceChunk method and with virtualized data sets. So we're kind of a little bit in the middle looking for kind of a sweet spot where we don't need to be, or sometimes if we don't want to be in US West 2, if we're in a different cloud provider, for example. But we want to utilize the benefits of those Zarr stores either locally on our own disk or from those remote sources. And we basically want to make it so that we can stream these chunks and we can take advantage of those cloud optimized data sets without having to basically regenerate this virtualized data set every time new data is added, or even if there are, let's say, occasionally there are reprocessing things that happen for granules that may have covered something from a long time ago. And you can see that with that VirtualiZarr and IceChunk method, it's very abstract concept heavy. So I'm going to try to walk through that a little bit here. And it's also a little bit computationally heavy. The benefit, though, with that is that with IceChunk, you can generate the VirtualiZarr data set once, and then you can simply just edit those individual chunks afterwards. And so that's what we're kind of looking for. is with this method C. Obviously, there are many different ways to do this, but this is kind of what we're looking for. Next slide, please. So let's take a look at what that typical workflow is for that direct ZARR access. So this is basically kind of without using that VirtualiZarr data set. Click, please. So first, you're going to utilize earthaccess to search for those collections that you actually want to analyze. You're then going to filter for those ZARR S3 URLs. And so then you can utilize Xarray to open those. If you click again, please. Once you open up that ZARR store, you're opening it from that remote source. You're taking advantage of that full scalability of the AWS cloud in the case of NASA Earthdata. And then you can simply perform that subsetting and analysis all with Xarray. Click, please. And once you do that, you can export those data cubes from Xarray into a format that then has to either be written to disk or written to a bucket. That is really beneficial because you can overwrite or add new data. You can export those calculated data values. But the only problem with this is that you could potentially double, triple, or just increase the amount of data that you're storing locally or in your bucket storage. So a way that you can optimize this is with VirtualiZarr. And VirtualiZarr simply points to those remote chunks. Thank you. And so, yes, you can go to the next slide and click there. So in the case of VirtualiZarr, you'll notice that I italicized the word generation because you need to generate that VirtualiZarr store if a kerchunk file reference file isn't present, and then access it. So in the case of building with VirtualiZarr, you need to search for the DMRPP file by collection. You do that with earthaccess.search data, and that contains the full CMR record. If you wanted to construct a custom VirtualiZarr data set using something that's not hosted in NASA Earthdata, you can filter out those different links. But the other thing too is that with the case of NASA Earthdata, we're actually just grabbing those HTTPS or S3 links based on where our cloud compute instance is. We're not grabbing OpenDAP links because we're not asking for another service to subset before returning that to us. We're actually just going to generate these references to those chunks in the cloud. And we do that using earthaccess and their DMRPP parser. If you click again, Amy. And so this is what Ayush Nag worked on with the OpenDAP folks, and we're able to get this included with earthaccess. And that's really, really useful because VirtualiZarr stores can handle a large amount of different formats, a large amount of variability of access controls. And so this basically simplifies your life much better. You can have much more fine-tuned access and generation with the actual VirtualiZarr API. But here, all we do is if we click load equals false, we simply generate those reference files. And then if you click again, Amy, you can save those to a reference file using kerchunk. And so that's what you heard Joe talk about. Those kerchunk files are very lightweight. They are in Parquet or JSON format, and they contain simply the references to the chunks of that data cube that is sitting in the cloud. So they do not contain any actual data. And as a result, you need that original data source to be accessible. If you were to, let's say, generate the VirtualiZarr store one day, come back to it another day, you can generate it locally. So you can manage a VirtualiZarr store on data that's on-prem, or it could be from a bucket. But the issue comes in when you need to edit a chunk without having to regenerate that whole VirtualiZarr store, and when you need to actually edit that reference file for later access. And that is where IceChunk comes in the next slide. So with IceChunk, what you're essentially doing is instead of regenerating that VirtualiZarr dataset, which can be very computationally expensive, it can take hours potentially to generate all of Mara 2 data, which we've experimented with before. What this does is once you've generated those kerchunk reference files, you can simply just access the actual chunks and edit them. And the way you do that is very similar to Git control. So you're basically committing edits to those chunks like you would for a code repository. And when you do that, you're essentially just managing the structure of the data cube itself without those managing those individual files. So instead of saying, well, I'm going to pull this granule and then edit that data. This is not that. So that's an option, but this is simply not that. And so if Amy clicks again, you'll see that I've got another really big reminder that says you're only editing and versioning the chunks. So no actual data is present in here. Next slide, please. So that leads to a couple of considerations. So there's lots of different documentation that I'll leave you all with, but when you're managing these, you're essentially playing the role of your own private data center. So it helps to, with the way that IceChunk is structured, to be familiar with that process. So it helps to be familiar with how you would access or generate that IceChunk repository. That IceChunk repository can live in a bucket locally. It's something that is really based on the scale or the application that you're trying to use. The other thing is that if you are generating that IceChunk store based on a collection that is constantly expanding, or maybe even have edits to it with different versioning, you need to somehow be in sync with those changes. And so it really helps to monitor any sort of NASA data center for alerts if there is, let's say, a correction to an individual granule here or there. What that basically allows you to do is just actually edit those individual chunks without having to change the full thing. The only thing about this is that, like I said, you're essentially having to replicate the role of kind of a data center. For the actual VirtualiZarr store generation, there are still lots of bumps along the way to getting that to work with the majority of NASA Earthdata collections. And so we would love for you all to just basically mess around with this, test generating those, maybe even test creating an IceChunk store, and drop us a thread in the earthaccess GitHub repository. And that's also where you can see all of our different discussions for all the different things that we're trying to figure out, where certain libraries should live, what's the best way that we can really make this easy to use, which is already something that earthaccess has been able to accomplish for even downloading or streaming individual granules. And then finally, it helps to know the pricing whenever you're dealing with any sort of cloud related thing. So if you are managing that IceChunk repository and writing it to a bucket in the cloud, you need to know the pricing, the free tier limits. You could potentially make somebody else a lot of money if you don't know what you're doing. You don't necessarily want to do that. And so that really helps to know. Also, the same thing with compute instances, the amount of cores or the way that you're generating the VirtualiZarr stores can be very computationally expensive. Next slide, please. And so without spending way too much time on this, what I wanted to do was get you all a few links that you can get started with if you access the slides. These documentation have been able to address a lot of different questions I have. So for example, we know that over at PODAC, some of those Kerchunk reference files are actually hosted and referenced. Is it possible to put those into an IceChunk store? It certainly is. And there's all sorts of different documentation on how to do that. So I've got different links there, different end-to-end examples that they have in the VirtualiZarr documentation, all sorts of different use cases as well. And then I also wanted to post those IceChunk documentation. So IceChunk is managed by the Earthmover folks. They have a variety of different APIs and different things that some are free, some of them are paid for. For example, with the Array Lake tool that they have a web application that you can use to kind of point and click manage those virtual data sets using IceChunk. It does require a little bit of consulting with the documentation to figure out any sort of cost or scale with those. And so when it comes to the earthaccess library, again, we're still kind of in the process of testing those. But if you stay connected to us over on the earthaccess GitHub forum, that's really the best way to stay connected with these changes. And so with that being said, I will hand the mic over to Danny. Thanks for driving, Amy.
Yeah, okay,
Chris.
so
yeah, Danny, do you want me to keep sharing? I'm happy to.
yeah, why don't we just do that? If
Okay.
you're okay with still clicking.
No problem.
Okay, sweet. Thanks. Just less transitions, I guess. So yeah, so in in this section, I was gonna share a kind of an example of testing and trying to get some of these virtual data cube methods working for a particular NASA mission, TEMPO. This presentation, which was not really a full presentation, it's a few slides that were put together to add to a discussion during ESIP. I think it's only 4 slides, so, and we are kind of short on time, so maybe that's for the best. So Amy, if you could click to the next slide. I'm gonna, on this slide, I wanted to give just wanted to give a background on this use case. TEMPO, which is a geostationary satellite that was launched in 2023. It's NASA's first geostationary Earth observing satellite. Measures air pollution during daylight hours, and because it's in geostationary, it means that it's always looking down at North America, and it kind of orbits at the same rate. So that way we can get repeated scans of North America and see how things change over time. So if you click again, Amy, the part where earthaccess and virtual data cubes comes into play is because this produces a ton of data, and like all of the other missions, we want to be able to get efficient access to time series, make it easy for folks to work with these data in an analysis mode. So the way TEMPO, the challenges for TEMPO, the way these manifest is that because TEMPO is geostationary and it scans east to west every hour, it produces approximately 10 granules every hour where it's scanning back and forth. All of these have these DMR++ files, which I think was already mentioned, at least in passing. These are reference files that were originally generated for OpenDAP purposes, but they have information about data chunks and the byte ranges for these chunks in S3. And so these provide an efficient means for grabbing chunks as if they were a virtual data cube. Yeah, Chris mentioned Ayushnag developed a DMR++ parser that then can be brought to bear for TEMPO. Just as a kind of sense of scale, a year's worth of TEMPO level 3 data amounts to about 5,000 granules. These are level 3 granules, so this is full scans, and it's about 2.5 terabytes. So that's a lot of data to work with in memory. Probably not going to be able to do it in memory. So next slide. So this, we wanted to, for TEMPO, we wanted to do some testing of these methods in earthaccess. So this Open Virtual MF dataset, which is the companion to Open Virtual Dataset, the MF standing for multi-file. This is the convenience function that on the back end uses the DMR++ file, uses VirtualiZarr to generate a virtual data set on the fly by going through all of the granules and reading the chunk manifest for all of them. Now, the testing, when testing this for level 2 granules, these are the geospatially derived measurements from the satellite, but they haven't been gridded. These level 2 granules fail to be opened as a virtual data set using earthaccess. And the reason for that is that because of the way the satellite puts together these granules, occasionally they will have different size dimensions, and this isn't yet allowed in the ZARR specifications. So because of that, the concatenation of virtual data sets fails for level 2. But if you click again, Amy, level 3, which are the gridded data products, this works. It works pretty well. We actually see an enormous improvement when we're trying to access the level 3 data granules as a virtual data set, only taking about on the order of 10 minutes, as opposed to downloading these data, which takes about a whole day. So on this slide, if you wanted to find more information, there's links to the GitHub issues and discussions that go into much more detail about why things aren't working, and show me trying to troubleshoot these in conjunction with other folks that have been gracious enough to add their thoughts. And at the bottom of that slide, there's a link to the tutorial notebook in earthaccess that shows how this works with level 3 data. Okay, next slide. So the level 3 virtual MF dataset using earthaccess succeeded in part because it, unlike level 2, it does have consistent dimension sizes, and like I mentioned before, Tempo has these DMR++ files generated already as the granules are being ingested into the NASA archive. The DMR++ files are available. If you click again, Amy. Now, these conditions are not true for all of the data in NASA Earthdata. So maybe my section of this talk is kind of like pointing out where there's still a lot of work to be done. Like virtual data sets are awesome and when they work, but there's a lot of caveats to when this won't work. So DMR++, this particular way of working with virtual data sets that relies upon DMR++ won't work for all data sets because not all of the data sets have DMR++. Did an assessment of the Earthdata archive, and there's a lot of caveats to even this assessment. This was done from my account. This was including certain like products that might not be shouldn't be available, like level 0 data that we probably won't need to create virtual data sets of. This also just checks single granules, but you can see the numbers here are referring to what percentage of the collections in NASA Earthdata actually either have those DMR++ files, whether they're downloadable, whether they're parsable, I think that's a word, whether they can be parsed by VirtualiZarr. And so if you wanted to summarize it, it's like something like 15% of the NASA data collections that might have DMR++ that could be worked with for this approach. Okay, next slide. This is my last slide. So just sort of as a summary, actually that's not a summary, but the summary is that the level 3 worked really well with Tempo because of the DMR++ and because it has consistent dimensions. What we're working on now is to create these combined reference files that using VirtualiZarr that don't rely upon the DMR++, and would provide access to the entire Tempo level 3 collection. Done some tests, and this has worked for smaller amounts of the time series for Tempo. Some of the things is that still need to be overcome are the data tree like handling of netcdf4 groups. So the hierarchical structure of data, which means that data variables are in certain groups. They're not all at the same level of the file. That makes things not quite as simple and as streamlined for users. Can be overcome for some of it, but sometimes it's really challenging. And then this variable length chunk, which is just another way of saying the inconsistent dimension sizes. And there are decisions to be made along the way as far as the format. A couple of these formats were mentioned: Parquet, JSON. There are decisions to be made about how should we store these, where should we store them, and then finally, I think Louise mentioned it in the chat, documentation and tutorials that actually show how to do that. It's not enough to just make this happen, but we're part of this earthaccess community that Amy started us off with, and that's a huge part of this, is being able to learn together how to do this and share our understanding. And that's all I have.
Thank you so much, Danny. It was great. So I know we're kind of moving into sort of discussion time. I think we're good. Luis, I know you have a few more slides to kind of bring it all home for us. Please, though, continue to add questions, thoughts into the doc so that we can jump right in and start having some discussion. But yeah, Luis, we'll hand it over to you. I can also keep sharing if you don't mind, or if you want to.
Yeah, that's perfect.
screen.
And I'll try to
Okay,
be
great.
short because I think questions and that is really important for us. So I always like this image from Alison Horst that designed the We're All in This Together. And building upon what Danny said about the community part of it and Amy said about the community part of it, I think we always consider earthaccess kind of like the place to like kind of trying to hack our way to fix the data problems that are more particular to NASA data than other providers. And I think we have succeeded in that in a way that I never thought it was going to be possible at the beginning. But thanks to all of you and more people that are not here in this meeting, I think we're like making our way through all of these problems. So next slide. And this is kind of like where earthaccess is currently positioned, right? And kind of like this is from JP Swinsky, a software engineer at Goddard, that said like, well, this is kind of like where we see these different levels of abstraction to get science done, right? In our time that everything has to touch a computer. So we have science users that are like organized in mostly cloud platforms or institutions that use some sort of like, well, cloud platform. I would say Jupyter would be the more prominent of those. And then they have to use some sort of like access to the data access tool. It could be a GIS tool or it could be a language. For us, that access is in Python mostly or entirely at the moment, unless you use like the wrappers for R that can talk to Python libraries. And then the idea of earthaccess also is to like integrate the system of mission-specific tooling and science data services that are out there. We currently have not tapped into that potential. We talk about it, and I think we will be working towards that. So at the end, the goal is to like, benefit the science users in one end, so they can take advantage of all the Swiss knife at their disposal. And thanks to all the people from different communities that have worked on getting these tools together, like Pangeo in particular, right? So that's kind of like our main set of tools for us in Python that makes all this possible. Next slide. I think we're in that moment, technically speaking, for earthaccess, that we're trying to like be smart about, and this whole talk was about how to be smart about accessing the data in the cloud. And I would say like, there is this approach of like, everything is kind of like very unorganized in the data archive. So let's start from zero, or let's create pristine ZARR data cubes. And that's fine if there is a mission that can afford to start producing ZARR, like in the case of It's Live, because there was nothing like, before that. So you can like start fresh and that's fine. But there are other missions that probably are like not operational anymore, or there are many constraints on like what kind of data should be produced, what kind of file has to be produced for many interoperable considerations. Then I think earthaccess is trying to bridge that gap on all the possible scenarios and trying to be smart about like, okay, so you want to ask a scientific questions, and either that be a time series or it can be like some operation that uses many files. We're in that moment where we're trying to implement something that will give you the best access pattern to that data. And so far, virtual data cubes is kind of the answer. The idea is that the providers will generate those cubes, not the users. But in the meantime, we have to do something, right? So in the immediate future, I think what we need to do is to deal with distributed authentication. Basically, earthaccess should take care of some of this stuff. It's doing too much because the data is not harmonized. And that's the next slide that I'm gonna talk about in a second. Yeah, so distributed authentication, optimize metadata rates, and optimize I/O. So we're talking about like replacing FSSpec with Upstore because it's more, it was designed, this is the driver that talks to the data in the backend. But we're not there yet because Upstore needs to meet some criteria. I don't know if we'll do it like in the next month or the next 2 months, but the ultimate goal is to like replace that paradigm of opening files into seeing, you know, like a logical data cube where you can ask your scientific questions without the users noticing what's behind the scenes. And that's kind of like the X-ray way of doing things and all of that. So that's is the way now, but it could be replaced by cube, or it can be a different way of scaling or computations. And the same 3 lines of code should be tried to preserve, well, we should try to preserve the simplicity of this. And finally, and this is really important, and Danny touched this point, well, this is in the next slide. These are words from Patrick Quinn, that until recently, he was the ASDC architect or the NASA software architect. He wrote a memo when kind of like the parting brain dump for him. And I cannot agree more on this. Like, we should stop trying to, you know, keep building tools, and we should start fixing the data as a data producer. Once that we do that, we won't have the need for building, you know, a ton of APIs that will kind of like, you know, try to, and this is not an easy thing, but we should try to, you know, shift focus that. And in black, you have what, that's what Patrick said. I just edited a little bit and I put it in a different color. So to me, the next or the ongoing mission for the library is to continue to bridge that gap between the status quo of the data on NASA data and that future cloud native analysis ready archive that we can like kind of, it's like do really fast analysis because the data is optimized and harmonized and all of that. So with that, I think, thank you for being here.
Thank you so much, Luis, and to all of our presenters. That was so great.